Hi guys. So talking about 9.1 now, heat and thermal energy. Um, looking at now, so heat a little bit different than temperature, and that's what we kind of need to keep in mind here. And that's kind of what this focuses on. So how are heat and temperature similar, and how are they different? 9.1a, explain what heat is, depends on, and the direction it moves. Explain why some materials hold heat better than others, and then calculate the change in thermal energy and specific heat is kind of what we're looking at with that one. So some calculations along with this section. So um, as we start here, get rid of that for us. Heat, temperature, and thermal energy. Heat is just thermal energy that's moving, so it's a transfer of thermal energy. Um, the picture here says, what makes that chocolate bar melt in your hand? Well, what is it? Well, the heat from your hand is traveling to that chocolate bar, right? The chocolate bar is room temperature. That's cooler than your body temperature. So heat from your hand is traveling to that chocolate bar, increasing its temperature and changing its properties. So heat flows anytime there is a difference in temperature. Difference in temperature means that heat is going to flow from high to low. Because your hand has more thermal energy than the chocolate, thermal energy flows from your hand to the chocolate, and the chocolate begins to melt. Not anything too crazy. Heat and temperature are related, but they are not the exact same thing. So in this example, we have two pots of water. They are both boiling. That means that they are both at 100 degrees Celsius. One of those pots is twice as big as the other one. That one is going to have twice as much thermal energy, meaning that one is going to take longer to heat up. It takes longer to cool down. It has more energy in it. If you just have a little bit of water, you can boil that little bit of water really fast compared to a lot of water. The amount of thermal energy depends on the temperature, but it also depends on the amount of matter you have and the type of matter that you have as well. Okay, so the amount of thermal energy, so these are both starred because they are both important. Heat and temperature are related, but not the same thing. Thermal energy, the amount of thermal energy depends on temperature. It also depends on the mass. It also depends on the type of matter. Okay, here we have two things of water. Okay, so that type of matter is the same. But if we have, a kilogram of gold at 25 degrees Celsius and a kilogram of water at 25 degrees Celsius, the amount of thermal energy in those would be different. And we're going to get to that. Okay. Joules are the unit that we use to measure thermal energy, just like we did with kinetic energy and potential energy. Um, but we were in the United States, we are not typically used to joules for the unit of thermal energy. We're going to use calories, and technically kilocalories. So 1 calorie is equal to 4.186 joules, and we are actually used to 1 kilocalorie, which is 1,000 calories. We could also use British thermal units as well, BTUs. Same joule that's used to measure all forms of energy, just not heat. Calories. Calories are the English unit that we use to measure thermal energy. 1 calorie is equal to the amount of energy needed to raise the temperature of 1 milliliter of water 1 degree Celsius. So I have 1 milliliter of water. I heated up 1 degree Celsius. It took 1 calorie of energy to do that. Specific heat is a property of that substance that tells us how much heat is needed in order for that substance to heat up. So water has a very high specific heat. It takes a lot of energy to heat up water. If you were to, well, just a simple question, if you were to put your pan on an empty pan on an oven or on a stove, and then a pan with water on the stove, which one's going to heat up faster? Well, the empty pan will, right? That water has a high specific heat. It takes a lot of energy to heat up the water versus a steel pan or an aluminum pan or something like that. Or if you is going to heat up much quicker than the water would in itself. Okay. Knowing the specific heat of a material tells you how quickly the temperature will change as it gains or loses energy. All right. So if we're talking right now about it heating up, but the same thing works in reverse. Once you heat up that water, it's going to stay hot for a while. A pan, I can expose it to some cool water and it's going to cool down really, really fast. It loses its energy just as quickly as it gains its energy. Okay, so the specific heat tells you how fast it loses or gains energy. It goes either way. So why is specific heat different for different materials? Like we already said, water has a very high specific heat. If you saw on the chart, the lowest specific heat listed on that chart was gold. So why because it takes so much more energy to heat up water than it does gold. We got to remember that what temperature is. Temperature is average kinetic energy per molecule. So it's the motion of those molecules. Now, when we put that energy into something, we put so much energy into it. If I have a kilogram of water and a kilogram of gold, I put the same amount of energy into it. Right? Gold has heavy atoms, they have fewer atoms. So that energy that I give it gets distributed amongst fewer atoms. In other words, those atoms get more energy on average, which is the definition of temperature, average kinetic energy per molecule, per particle, right? So when I give them the same amount of energy, gold has fewer atoms to equal that 1 kilogram. So those fewer atoms get more energy. I like to explain it with pizza. If I've got a class of 24 people and a class of 4 people, I give them each a pizza. Well, the class with 4 people is going to get more of that pizza. They get more of that energy, right? Class with 24 people, they hardly get any energy per particle, right? So that's kind of how I like to explain it. And more molecules, more particles means lower average kinetic energy when they're given the same amount of heat. So this picture kind of explains that. Here we have silver atoms are bigger, aluminum atoms are smaller, right? So it takes more aluminum atoms to equal 1 kilogram than it does silver atoms to equal 1 kilogram. Therefore, it takes more energy to raise the energy of each molecule up to a certain point, right? Remember, temperature is average kinetic energy per molecule. So if we wanted to raise the temperature of both of these things to the same, well, we need to give the one with more molecules more energy so that they have the same energy per molecule. Okay, so they have a higher specific heat. Silver has a low specific heat. What that means is that silver will heat up quickly and it will cool off quickly. So energy is spread over fewer atoms with silver. Each atom gets more energy and it will get higher temperature gain per molecule than aluminum where that energy is spread out over more atoms. That means less energy per molecule, therefore a lower temperature gain. Here is our equation for this. And in your references, there is that equation worksheet. Energy equals mass times specific heat times the change in temperature, T2 minus T1. I'll probably make a separate video showing you how to do these calculations. But this is the equation. Mass should always be in kilograms. Specific heat is going to be in joules per kilogram degree Celsius. And temperature will be that final temperature minus the initial. What we're really looking for is the change in temperature. Okay? And that is if we are measuring energy in joules. Now we can also change that to calories, and mass would be in grams, specific heat would be in calories per gram degrees Celsius, and temperature would still be in degrees Celsius. And that is all I have for these. Like I said, I'll probably make a separate video here going through some example calculations for you.